Hello. Hello. It seems that I'm audible. Now let us begin. I told that I would be providing examples, right? So that's why I'm beginning from CSP once again. So formal representation of CSP. Given a problem, how do we convert it to CSP? How do we represent it using symbols? This is the same generic question, the color mapping question. Color the regions of Australia such that the adjacent regions have different colors and use only three colors, red, green or blue. So in CSP, we know there are three things, right? Variables, domains, as well as constraints. So we'll be converting this problem into CSP using these three things. So here variables are nothing but the regions. We have 1, 2, 3, 4, 5, 6, 7 regions. So we have 7 variables. You can name them whatever you want. And we'll have, since we have 7 variables, they will have, there's supposed to be 7 domains as well. But in this case, each variable is allowed to take the same set of colors, red, green, blue. So all the domains are same, all the 7 domains are same. So I just wrote it once. But it need not be the case that it's always the same. In a more general case, the domains could be different for each variable. And constraint, if you look at the problem said adjacent regions should have different colors. So how do you represent it using symbols? Now that you've declared your variables, you use those variables to represent the constraints. How do you use them? You just take adjacent variables or regions and say they should not be equal. So WA and NT are adjacent, so you just write WA not equal to NT. So that would ensure that whichever value enters WA, the same value cannot enter NT. So that way you ensure that adjacent regions don't have the same color. So this is the exhaustive list of constraints. Yesterday I just gave 2 constraints, but this is the exhaustive list. You can check. This list of constraints covers all possible combinations. WA, NT, WSA, NT, all possible combinations. Fine, this is just the problem representation. Now, yesterday we talked about what is an assignment, right? Complete assignment, consistent assignment, so on and so forth. An assignment is nothing but the state of the problem. So we'll look at some examples. So let's say this is a CSP. So let's assume this is some CSP. You have some variables. You have, even in this case, the domain of each variable is the same. So I just wrote it once. And then let's say you have a set of constraints. So this is your CSP, for example. Let us look at some examples of assignments. So what is assignment? You just take a value from the domain and assign it to the variable. So that makes it an assignment. So you can have n number of you can use n number of variables. So in this assignment I used 2 variables, but in total I have 3 variables. So this makes it a partial assignment. And if I assign a value to every variable, it becomes a complete assignment. Now this is irrespective of whether the constraints are being satisfied or not, because if you look at this is violating the A greater than B constraint, but it doesn't matter because we are not claiming this assignment to be consistent, right? So coming to consistent means if any assignment satisfies all the constraints, it becomes consistent. For example, look at this: A equal to 3, B equal to 2. Here A is greater than 2. It is satisfying the constraints, so it is a consistent assignment. But it need not be the case that it need not be complete. Essentially, there is no value given to C, but it still satisfies the constraint, so it's a consistent assignment. In the case that an assignment is both consistent and complete, then that assignment is called a solution. Constraint graph is basically all your nodes are variables and all the edges represent the constraint between those two variables. For example, if you take the first two constraints, it's in between WANT, WASA. So you write the nodes, and then this constraint is represented by these lines. This constraint represents this line, this constraint is represented by this line. And if I take the next two constraints, I will add more edges, and then it goes on. So basically, what you get at the end is you get the constraint graph. Each edge represents a constraint. You don't have to explicitly mention what those constraints are. You can just leave it this way. Don't forget to add t. T is outside because it is not a part of any constraint. That's why there is no edge on t. But if you notice, these are binary constraints. Binary constraints in the sense, in every constraint you will find only two variables. But what if there are more number of variables? For example, look at this. In this constraint you have three variables. So this is a higher order constraint. It's not binary. How do you draw constraint graphs for those? Yesterday I didn't tell you how to do this because I didn't know it myself. What you do is, there is a trick. You just draw a square or rectangle of some sorts and join all the variables to that box. So this box now represents the higher order constraint. And if it's just binary constraint, as usual, you just make edges. That's it. Anyways, so if you open the slides, there's some theory about different kinds of CSPs and constraints. So different kinds of constraints means unary, binary, higher order constraints. CSPs, you have discrete, continuous, finite, infinite, all those. And yesterday I showed you how does a search strategy, how does it look like? How do you use a search strategy to solve a CSP? You'll get a search tree, so on and so forth. There'll be a node, you will have to find its neighbors. All that theory I've told yesterday. Now we'll look at an example. So let's say this is our CSP now, a simple CSP problem. You have variables, domain, and constraints. So search strategy, there are many search strategies. Let's use DFS for the sake of it. And there's another name for DFS. So backtracking, we'll come to backtracking later. It'll pop up once again. You can use any search strategy, because yesterday I've told you how to make a search tree. If you have a node, how do you find neighbors and so on and so forth. On that search tree, you will be performing some search strategy, something like DFS, A star, or whatever, up to us. So here I'll be using DFS. So initially, if you remember, the initial node will contain no assignments. And what would its children contain? Or neighbors, let me say neighbors. Its neighbors will have, how are you supposed to make the neighbor? You have to find that variable, find one variable that is not unassigned. Find that variable that has not been assigned any value. So if you look at this node, no variable has been assigned anything. So you can pick anything. Here I'll pick A. So A is my unassigned variable. I will assign it some value. The domain of A is 1, 2, 3. So I will make 3 neighbors, 3 children, because there are 3 possibilities. A could take either 1, 2, or 3. Now DFS, no. So what happens in DFS? Now I will expand A equal to 1. So when I expand A equal to 1, I'll have to, how will I expand A equal to 1? I'll have to find another variable that has not been assigned any value. B and C remain. So I'll pick B. After I pick B, what am I supposed to do? Assign value to B. So B could take 1, 2, 3. But DFS, right? So I will be at B equal to 1. Now the problem is, if you look at the constraint, A greater than B is not being satisfied here. So you cannot proceed with B equal to 1 because it is pointless. The constraint is not being satisfied. So you backtrack to equal to 1 and move on to the next child. Here also, but the same problem is here. A is not greater than B. So you prune that branch, you backtrack to equal to 1, and then you go to the next child. This is how DFS works, right? But even here it's the same problem. So you backtrack to equal to 1. Now you have no other choice but to backtrack to the previous node. So it seems like this entire branch has been pruned. Anyways, so a equal to 1 is pointless. There's no consistent assignment. Now that you've backtracked to node, then you explore. Now that you've backtracked to the initial node, you continue expanding from a equal to 2. So a equal to 2. Then the next unassigned variable is b. So b equal to 1, b equal to 2, b equal to 3 are its children. Since it's DFS, I will keep moving like this. B equal to 1, right? So the next unassigned variable is c. So I will assign c equal to 1, c equal to 2, c equal to 3. Since it's DFS, I'll come to c equal to 1. Now, but the problem is there is a constraint that says b should not be equal to c. But here b is 1 and c is 1. That's a problem. So you will backtrack to b equal to 1 and you'll check c equal to 2. But then the problem here is there is a constraint that says a not equal to c. Here a is 2, c is 2. So you can't stay at c equal to 2. So you backtrack and go to c equal to 3. Now there is no issues because here a is greater than b is not equal to c, a is not equal to c. So you can say this is your solution and you can terminate your search. So this is solving CSP using some search strategy. I took DFS specifically because this should show you backtracking, because backtracking will come later as well. There are other ways to solve CSP as well. There's something called generate and test. I think it's like a common, like many algorithms come under generate and test. The common idea is this. What you do is you generate all possible assignments. So it is called assignment space. All possible combinations you generate without checking if it is consistent or not. After you generate all possible assignments, then one by one you check if it is consistent or not. And then you keep returning the consistent assignments and tell that those are the possible solutions. Here you see it's a very inefficient way of finding a solution. Here you don't prune, nothing is happening. It's like brute force of some sorts. You generate all possible combinations and one by one check if the solution is consistent or not. That is generate and test. Constraint propagation. We will be coming back to constraint propagation, but it essentially it deals with domain reduction. We'll look at some examples. We've seen how does backtracking work. We've seen using DFS. They're essentially the same. Now there are ways in which we can improve our backtracking search. When we were doing backtracking, for example, when we started at the initial node, we had a choice. We could either choose the variable a, b, or c. Now, since a comes before b and c, we chose a. There's no reason here. But there are some methods that could possibly improve backtracking, and those methods will dictate which variable you're supposed to choose, which value you're supposed to assign to those variables. So we look at those methods now. How do you improve backtracking? So there are two questions: which variable to choose, and once you've taken a variable, which value are you supposed to assign? So first we'll answer which variable to choose. There are two rules within this which variable to be assigned next. One is minimum remaining values, the other is degree heuristics. If you look at the example, it would be much clear. So let's look at this CSP. There's a constraint graph. The current state of this problem is this one. B is assigned 1, D is assigned 2, and then if you look at the unassigned nodes, you have A, C, E. The domain of A is 1, 2, 3. C can possibly only take 3 because if it takes 1, then think of this as this one, map coloring problem. The adjacent values can't have the same value, right? You could think of it that way. Assuming that is the constraint, here you can't put 1 or 2 because 1 is here, 2 is here. So only 3 is possible here. And if you look at this node, 2 is here, so you can't put 2. The only possible values you can put here, use here is 1 or 3. Now, minimum remaining value states that you have to choose the variable with the fewest legal values. If you look at the unassigned variables, A has 3 legal values possible, C has 1, D has 2. You can see A has 3, C has 1, E has 2. So what does minimum remaining value say? It says choose a variable with the fewest legal values. So C has the least number of legal values. So you will assign C. You will pick C and then you will continue with your assignment. But there are cases where this will not always work. For example, if you look at this example, if you look at the unassigned nodes, A has 3 remaining values, B has 2 remaining legal values, and C has 2 remaining legal values. If you see, there is a tie break. If you try to use MRV and try to decide which variable to assign, which variable are you supposed to assign some value next, you'll realize that there's a tiebreaker. Should I choose B or should I choose C? So here comes the second rule called degree heuristic. You choose the variable with most constraints on remaining variables. So let's see. Let us count the number of constraints on other variables. A is here. There is only one constraint. See, this is a constraint graph, right? Every edge represents a constraint. So A has constraint on only B. B has constraint on A, D and C. So it has 3 constraints. C has a constraint on D as well as B. So 2 constraints. Now the tie break was in between B and C, right? So within B and C, we will look at the variable that has the highest number of constraints, because that is what it says, right? Degree heuristic. Now choose the variable with the most number of constraints on remaining variables. So here clearly B is the winner. So you will assign B next. So your next assignment should happen to B while doing backtracking. So we've looked at 2 ways. First way is to choose the variable according to MRV. The other way is to use degree heuristic in case MRV has a tiebreaker. So these 2 rules should help you decide which variable to be assigned next. In case there is some sort of a tiebreaker here also, it doesn't matter, take some random value within the tiebreaker, not outside the tiebreaker. Okay, now that we've decided which variable to assign a value to, now which value should be assigned to that variable? There's only one rule here. The rule is least constraining value. It says value, you have to choose that value that rules out the fewest values in remaining variables upon assignment. That's a mouthful, but now we'll look at an example. If you look at this example, this is this is the exact, not exact. This is a problem similar to map coloring. The same constraints are there. No 2 adjacent variables can have the same value. So let's suppose we are planning to assign a value to variable D. Let's say it is fixed. For the sake of this example, let's say we are going to assign a value to variable D. Now which value should we assign? If you look at its possible remaining legal values, I can either put 1 or 3 here because 2 is already here, and poor C can only take 3, and E has no restrictions because nothing is here, so E can take 1, 2, 3. So this is the current state. Partial assignment, because only A and B are assigned. This is the current state. So D has 2 options. It can either take 1 or 3. So let us look at both of these possibilities. What will happen if D is 1 and what will happen if D is 3? If D is 1, then E cannot take 1 and C still cannot do anything. It's just 3. So domain of C was 3. Now also it's 3. Nothing happened. But if you assign D as 3, E cannot take the value 3. That is fine because 3 is assigned here. Now the problem here is C cannot take any value because 1, 2, 3 are are already assigned to the neighbors of C. Now C has no legal value remaining. Now we look at some numbers. If you look at the number of values before assignment, C had only one value. Only one value, one legal value was remaining, and for E there were three legal values before assignment of D. So 1 is there, 3 is there, 1 is there, 3 is there. But after assigning D equal to 1 and D equal to 3, what happened? If you look at the number of remaining legal values at C, it is still 1, so nothing happened here. But number of legal values of E reduced by 1. It used to be 1, 2, 3, now it's just 2, 3. So remaining values are 2. If you look at the other case, C used to have one legal value remaining, now there is 0, so that's there. And the same story for E, 1, 2, 3 became 1, 2. So you only have 2 legal values remaining. Now if you look at least constraining value, what does it say? You have to choose that value that rules out the fewest values in the remaining variables upon assignment. So let us count how many values were ruled out in the remaining variables. So if you add this, you'll get the number of values ruled out, right? So 0, 1. So one value was ruled out from E. E had 1, 2, 3. Now it's just 2, 3. So one value was ruled out. But if you look at the second case, C had some value, some legal value that has been ruled out. E had 3 legal values, but one got ruled out. So 1 plus 1 is 2. So now which value should you assign? D equal to 1 or D equal to 3? If you look at it, 1 is less than 2. The number of values ruled out in the first case is less than the number of values ruled out in the second case. So you'll have to choose the first case, which is D equal to 1. But there is a simpler way of looking at this. Instead of looking at the number of values ruled out, you can simply look at number of values remaining. So number of values remaining means you just have to look at these values. After assignment, how many values are remaining? For the first case, 1 plus 2, 3 values are remaining. In the second case, 0 plus 2, 2 values are remaining. You have to pick the highest number of remaining values. This also works. So finally, you have to assign D equal to 1. So D equal to 1 or D equal to 3, after looking at least constraining value, we are able to finalize that D equal to 1 is the appropriate assignment. So that is how we improve backtracking. So there is an example. This is the exact same map coloring problem of Australia. This is the constraint graph. So initially no node has been assigned any variable. So how do you decide which variable to pick up? First rule is MRV, minimum remaining values. But if you look at every node has exactly 3 legal values. So there is nothing minimum. Everything is a tie break. If there's a tie break in MRV, you have to look at degree heuristics. What does degree heuristic say? Just pick the variable that has the most number of constraints on other variables. So it is very much obvious that this node has more number of constraints on other variables. So you'll have to assign this node. So you have to select this one. So after you select this node, then you can assign R, G and B. You'll get 3 children, R, G, B. Backtracking is essentially DFS. So what you'll do is you will start expanding this state. Now if you look at minimum remaining values, you still have a tie break because here 2 is remaining, 2, 2, 2, 2, 3. 3 is not minimum. So there is a tie break for MRV once again. So you look at degree heuristics. But there's a tie break for degree heuristics as well. This has 2 degree, like you have 2 constraints. This has 2 constraints, but the maximum is 3 here for the unassigned nodes. 1, 2, 3. This node also 1, 2, 3. This node also 1, 2, 3. So there is a tie break for these 3 unassigned variables. Since there is no other rule, so you can pick something randomly. So I will pick this one randomly. So I'll pick this node and assign it a value. Since R is here, this can either take G or B. So there is G, there is B. You can check LCV also. You'll realize there is no issue with LCV at the moment. You can check what will happen if you put G here, if you put B here, like we did for this one. Which assignment is following LCV? You can take that value, but in this case, no problem is there. You can check by yourself. There's no problem here. Because if I put G or B, the same number of values are getting ruled out, so nothing has the least number of ruling out. There's nothing like that happening. Anyway, since it's DFS, now I'll explore this one. So which variable should I choose next? I have to look at MRV, but then MRV, there is a tie break. All of these nodes have minimum legal remaining values 2. Everything has only 2 remaining values. Then you look at degree heuristics. These 2 nodes have the same number of degree heuristics, the maximum degree heuristic. There's a tie break once again. Then choose randomly. So out of these 2, I took this one randomly. And there is only one child to this because only one value could be assigned to this, because R is here, G is here, only one possible assignment is there. So this goes on. Now I think you can continue with this. You keep checking MRV. If MRV is a tie break, you look at degree heuristics. And if degree heuristics is also tie break, pick randomly within the tie breakers. And keep checking for LCV also. Which value are you supposed to assign? In this example, LCV, there's nothing much. This LCV was not used because if you check the LCV condition, there is no change. You can check it by yourself. Anyways, that was backtracking, and then there's forward checking. Forward checking is something that is slightly better than backtracking. What does it do is, it does this, exactly this. Keep stack of remaining legal. So we look at an example. So let's take this simple CSV and let's do forward checking. If after you look at forward checking, you'll realize why is it better than backtracking. So what do? Is you begin with you begin with all the variables and its domains. So A domain is 1, 2, 3, B domain is 1, 2, 3, C domain is 1, 2, 3. Now what you do is you assign a value to one of the variables. So let's pick A. If you draw the constraint graph here, it will look something like this or something, right? It will look this is okay, fine, that is constraint network. Anyways, so constraint graph of this will look something like this. You have A, B and C. This will be the constraint graph. So anyways, so how does forward checking work? I told you, right? You start with all the variables and its domains side by side. Then you pick one variable and assign it all possible values. So A equal to 1, A equal to 2, A equal to 3. But after assigning the values, what you're supposed to do is you have to eliminate those values in the domains of the other variables, which makes the assignment inconsistent. For example, once I assign A equal to 1, that would mean A should always be greater than B. So I have to remove all the values from the domain of B that violate these constraints. So if you look at B equal to 1, and in this case A is already equal to 1, right? So if A is equal to 1, can B ever take the value 1? No, because 1 can't be greater than 1. 1 can't be greater than 2. 1 can't be greater than 3 as well. So that would mean I'll have to remove all the values from the domain of B in this node. And forward, now that there is a node that has an empty domain, when you reach an empty domain, when a node gets an empty domain, you stop forward checking. So you prune that branch and then you backtrack and go to the next node. I'll tell you what happened once again. You start with all the variables. These variables are unassigned. These are the domains of each of the variables. Domain A, domain B, domain C. You begin forward checking by assigning one value to one variable. So I picked variable A and assigned it 1, 2 and 3. I branched out. Now this is similar to DFS. You will explore similarly like DFS. So I'll first check this one. If A is equal to 1, what I'm supposed to do is I'm supposed to remove all the values from the domains of B and C that conflict with A equal to 1 with respect to the constraints. So the new domain of B is empty because I can't put B equal to 1 because A can't be greater than 1, A can't be greater than 2, A can't be greater than 3 as well. So no possible, there's no value in B that could satisfy A or that could be consistent with A. So that is how you reduce the domain. So this is a form of domain reduction. You're reducing the search space. But in forward checking, this there's a condition. If any node reaches a stage where one of the domains becomes empty, you stop forward checking. So you stop forward checking, you backtrack and go to the next stage. So in this next node, what is there? A equal to 2, right? If A equal to 2, what are the values of B that would be consistent with A? If A is equal to 2, 2 can be greater than 1? Yes, so B is allowed to have 1. Can 2 be greater than 2? No. Can 2 be greater than 3? No. So the values 2 and 3 are removed from the domain of B. Similarly with C, A can't be equal to C, right? So from the domain of C, the value 2 is removed. So C domain becomes 1, 3 in this node. Since it's DFS sort of a thing, I will keep exploring this now. Next, I will assign the value to B, to variable B. There's only one value, so I will assign it the value. Now I'll check if there are any values in C that violates the constraints. So if A is 2 and B is 1, A greater than B is satisfied, that is there. B not equal to C. If B is equal to 1, then C can never take the value 1 because constraint states that B not equal to C. So you have to remove the value 1 from the domain of C. That's why in this new node, C domain is only 3. You don't have 1. And this node is also complete. Now you will assign the value to the next unassigned variable, which is C here. There's only one value remaining, so C equal to 3. If you reach an end in forward checking like this, it means you've reached a solution, a consistent and complete assignment. You could possibly backtrack and explore other cases as well, but I stopped here because this is the procedure. You can continue with the procedure. So this is some form of constraint propagation because there is some form of domain reduction happening, right? You're reducing the domain while you keep searching. Now the reason why this is better than backtracking is that in backtracking, if you notice, we had to prune this branch only after assigning B equal to 1, B equal to 2, B equal to 3. We had to go through all of that before realizing that the assignment is useless. But if you look at forward checking, before assigning anything to B, we were able to prune this entire branch where A is equal to 1. So it's like one step ahead. That's why forward checking, it looks ahead in some way. Fine, that was forward checking. Constraint network is basically you modify your constraint graph. How do you modify your constraint graph? You replace the edges with two edges and a rectangular box where you specify what the constraint is exactly. This is how the constraint graph looks like. So you replace each of these edges with these rectangles, and then you mention what constraint is there between each of those two variables. For arc consistency, there is a nice short video which is there. You have to go to Friedenker's folder, and within that there is a folder called AI stuff. You'll find a nice video. It's around 7 minutes. I think 5 minutes of that video or even less is AC3. So you can watch that video. It is a short and nice video. Path consistency, just look at the slides. I don't think any example was given, but you can look at path consistency on your own, because no algorithm was mentioned regarding path consistency. For arc consistency, there is an algorithm. You can look at the video. For path consistency, you can only check if the assignment is path consistent or not. The rules to which are provided in the slides, and I'll not be providing them here. So that was CSP. Next, I'll be moving on to probability and naive, Bayes model and all those things. So there are some points to remember. So if let's say cavity, right? If it begins with a capital letter, it is a random variable, and if it begins with a small letter, it is a proposition. Which proposition? This proposition. The random variable is equal to true. So this proposition can be written as this word. So it's just like a shortcut way of representing this proposition. What is a proposition? A proposition is a statement. It is either a true statement or a false statement. So cavity is true. It's a proposition. Okay. And Boolean means, true or false, right? So it's a variable. I can either assign it true or false. Anyways, so this is what I'm talking about. So cavity, random variable cavity equal to true can be written in short as cavity in all lowercase. So let's assume it is 0.1. So what would cavity equal to false be? 1 minus 0.1, which is 0.9. This part is fine, but the other part is, now we'll be dealing with a vector of probabilities. So instead of writing random variable cavity equal to true or cavity equal to false, I will simply write the random variable, probability of the random variable cavity. Since it can either be true or false, you will get a vector of probabilities. So the vector, how does a vector look like? A vector looks like this, no? To write it horizontally, they use some weird notation, but vector is essentially this one. So what does the vector represent? The first element will represent the probability of cavity equal to true. The second element will represent the probability of cavity equal to false, which is very much evident here. So there are cases where this vector, if you add the elements of this vector, you might not get 1. In those cases, alpha will play a role. In this case, alpha is 1. So alpha is there to normalize the vector. That's it. You look at some more examples there, you will see alpha playing a role. So let's say whether is one more random variable. So probability of a random variable is a vector of probabilities. So let's assume weather, there are 4 kinds of weathers: sunny, rain, cloudy, snow. So you'll get a vector that is like this, a 4x1 vector. you get a vector. And then you people know joint distribution, joint probability distribution. Now you have two random variables. Now you'll have to look at all pairs. So sunny, cavity, sunny, no cavity, rain, no cavity. So you'll get a matrix. There are four kinds of feathers, and since cavity is a Boolean variable, you'll have true or false. So you have two kinds of answers there. So 4 into 2, 4 cross 2 matrix is what you'll get. And then if you see a comma, it usually means and. So don't get confused. And now these are some formulae that we'll be using in places. So probability of A given B is nothing but probability of A and B divided by probability of B. You can rearrange the terms and get this one. And this is a generalized form. Probability of A and A1 and A2 and A3 is nothing but probability of A1 and then probability of A2 given A1 and then probability of A3 given A1 A2, probability of A4 given A1 A2 A3, and so on. It goes on. Now there's something called Bayes rule. Bayes rule looks like this. So probability of B given A can be written as probability of A given B into probability of B divided by nothing. You just use these rules and then you can derive Bayes rule as well. But the places where we use Bayes rule is this one. You can look at some examples. They're very much simpler. We did Bayes rules many times, so I'll not be covering an example for Bayes rule. It is simple. Now the thing here is, this is like it is given that C has happened. So this is like a modified form of Bayes rule. There's nothing much. Everywhere the only change is C. It is given that C occurred. So this is like Bayes rule, but given C has occurred. And usually in Bayes rule, the denominator might not directly be given. You might have to do some summations. If you remember total probability from the previous semester, you would know. Or maybe just look at an example, you will understand what is happening. Okay, ignore this part. There's nothing for me. Nothing for you people here. There's a doubt that I had, so I just strike this place off. Let us look at an example. Let's say this is some probability distribution. You have three things. You have toothache, you have catch, you have cavity. So we have to find what is the probability of random. See, look at the capital letter. Random variable cavity given to toothache. Here toothache is it's all in lowercase. So this means tooth. What does this mean? This means toothache is nothing but true. Here toothache is true. Random variable toothache is true. That is why I can write it in short form. Small toothache. Using the rules of probability. How do I write A probability of A given B? It is nothing but probability of A and B into probability of B. So what I did here is I've converted the probability of toothache to alpha. It is some constant, so I just wrote it as alpha. Probability of toothache I've written it as some alpha. It's some constant here. So now I'll be expanding probability of random variable cavity and toothache. But it's not just toothache and cavity, right? There's something called catch. But there is no information given about catch here. So there are two possibilities. It is either catch or not catch. So this is how I'll be splitting it. Probability of cavity comma toothache became probability of cavity, toothache and catch, probability of cavity, toothache and not catch. This probability of toothache is written as alpha. It's just a constant. You can compute it later. But if you remember this part, probability of a random variable will give you a vector of probabilities. So that is what is going to happen here. You have a random variable here. This cavity is a random variable. It does not begin with a small letter, so it's a random variable. So how do you represent this random variable in terms of how do you represent this probability of random variable? You write a vector, a 2 by 1 vector. The first element will be the probability if cavity is true, and the second element will be if cavity is not true. So in short, I can write small cavity, lowercase cavity, and not lowercase cavity. So first element represents cavity equal to true. The second element represents cavity not equal to true. So cavity false. So not lowercase cavity means random variable cavity is false. Same goes for the other probability of random variable as well. So you get two vectors here, and alpha is still outside. And then looking at this table, now it's easy to fill in the numbers. So you fill the numbers looking at the table, and then you add it up, you will get a vector. Now alpha, if you remember, I told alpha is nothing but the constant of normalization. So it will normalize the vector. How will it normalize the vector? If you have a vector like this, in order to normalize it, you have to multiply it with 1 by the summation of those two elements. Then it will get normalized. So if you perform the math, if this becomes 0.2, if you multiply 0.2, you'll get this one. And if you sum these elements, you'll get 0.6 and 0.4. You might be thinking, how is probability of toothache equal to this? You can check it by yourself. I think you can once check. All the math will somehow lead to this only. So it's like in general, whenever you have a probability of A given B, you will write it as probability of A into B, a probability of A and B, and then you'll multiply it with some alpha. And that alpha will usually just turn out to be the normalization constant. And there is something called independence, and there's something called conditional independence. So if probability of A given B is nothing but probability of A, or if probability of A and B is nothing but the product of probability of A and B, then that would mean A and B are independent, and it is represented like this. But let's say instead of just A and B, there is something else. There is C as well. Everywhere it is stated that C is given, C happened. And in only those cases, you have something like this. So what you do is, for your independence, whatever is there, you just add C everywhere. Here C you add, here C you add. If you do that, then it becomes conditional independence. Why conditional independence? Because it looks as though just because C is there, only then are A and B behaving to be independent. So something like that. If C is not there, we don't know. But since C is here, we can say that A and B are independent. So this is a form of this is conditional independence. So given C, A and B are independent. That is the meaning of conditional independence. Given C, A and B are independent. Because if you remove the C, it becomes the original independence equations. Next is naive Bayes model. What you have in that is you have some n random variables which are mutually conditionally independent. Now when I say conditionally independent, you're supposed to give something, right? Something is supposed to be there. Here I told C, but in the naive Bayes model, let's assume it's H. So given H, all these n random variables are mutually independent. So basically they're all conditionally independent given H. Now what does naive Bayes model have to say about this? What does it says? Given this piece of information, you can find out the probability of this one. Probability of x1 and x2 and x3 and so on until xn and h. The theory kind of says that x1, x2, x3 they all represent some form of symptoms, and h is nothing but the hypothesis. And now you want to predict what is not. You want to find out what is the probability of all these things. A neat formula is given. I'm not deriving the formula. The formula is nothing but the probability of h into the product of all this xi given h. So it will look like this: probability of h into probability of x1 given h into probability of x2 given h, and so on till probability of xn given h. This is naive Bayes model. The assumption is that x1 till xn are conditionally independent given h. Given this assumption, this formula will work. So symptoms, let's say you are diagnosing some medical issue, then you can use this model or something like that. And then you have some theory about advantages, problems and issues. You can go through the slides. So next is Bayesian networks. Bayesian networks. So this is like a summary of some sorts. So a Bayesian network will look like this. You will have a directed acyclic graph. So you will not find cycles. Directed, so you'll have arrows like this. So at the top you will have some random variables to which there are no edges that are coming to it, right? No arrows, no inward arrows. So those random variables are they're marginally independent. They are just there. Nothing causes it. It is independent. If you look at the diagram, you'll understand. And then there will be some other variables that will be in between. So C is dependent on A and B, and D is dependent on C, E is dependent on C. So these arrows represent direct dependence. But if you look at D and E, both of them are dependent on C. So this is where the conditional dependence comes in. So D is dependent on C, E is also dependent on C. So D and E are conditionally dependent given C. So if C is given, these two random variables are dependent conditionally. And in a Bayesian network, each random variable will be associated with a probability distribution. You will look at it in an example. And if you look at something like this, one random variable after the other, one gives rise to the other. So that is called Markov dependence. This structure will be more prominent when we come to Markov chains or Markov processes. But we'll look at some examples. How do we write the probabilities concerning this Bayesian networks? So let's say you have something like this. You have no arrows. You just have A, B, C. They're all marginally independent. Nothing is there. No arrows. So the probability of the random variables A, B, C. So A and B and C. You simply have to write probability of A into probability of B into probability of C, because they're all independent. We know, if we've seen independence, no? Probability of A and B is probability of A into probability of B. Since A, B, C are independent, so probability of A, B, C is nothing but probability of A into B into C. Let's say the graph looks like this now. The Bayesian network looks like this. Now how do we write the probability of A, B, C? you start writing from the bottom. So you start from probability of B. When you write probability of B, just look at the random variable on which it is dependent. So B is dependent on A. So you have to write probability of B given A. Now after you write B, you write C. So probability of C. But C is dependent on A. So you write probability of C given A. Now after C is also done, you look at A. You have to write probability of A. But probability of but A is not dependent on anything. So you simply write probability of A. So if you are given a graph like this, the probability will be this. We will see where to use these things in an example that will come later. But given a certain graph, this is how you write probabilities. You're simplifying, no? You're splitting it into smaller components. Now let's say you're given a graph like this. Again you start writing from the bottom. You start from C. C is dependent on A and B, so you write probability of C given A comma B. So C given A comma B. So both are given. And now after writing C, write A, probability of A. There is no dependence, so you just write probability of A. Then write probability of B. You're done. So okay, now this is Markov dependence, right? But it's still a Bayesian network here, at least. So when I said right from the bottom, what I wanted you people to do is, if the arrow is moving in a certain direction, start writing from the opposite direction. So here the arrow is moving rightwards in this Markov thing. So you start writing in the opposite direction. So you start from C. So probability of C, write probability of C, but C is dependent on B. So you write probability of C given B. Now C is done. The next write probability of B, but B is dependent on A, so you write probability of B given A. Then you write probability of A, but A is not dependent on anything, so you simply write probability of A. So this is how you write probabilities. Now we'll look at an example. We'll look at a Bayesian network. So this is a Bayesian network. This is like a proper example. You have a Bayesian network. You have all the random variables, and each random variable is associated with a probability distribution. How did we get these numbers? It's already given in the question. They either come from observations or from expert knowledge. So you have B, burglary, earthquake, alarm, John calls, Mary calls. They're all random variables. That's why they're in capital letters. Random variables will be written in capital letters. Since B and E are marginally independent, they don't have much to say. It's just that you just have probability of B is 0.001. So probability that there's a burglary is 0.001. Probability that there is no burglary is 1 minus this one. So you'll get 0.999. If you want, you can write that as well, but it's not required. It is understood. Same goes for probability of earthquake and probability of no earthquake. And A is dependent on B and E, right? So depending on the combinations of B and E, the probability of alarm will keep changing. And J depends on alarm, so depending on alarm, probability of J will change. And M depends on alarm, so depending on alarm values, probability of M will change. So here the problem is, you can understand, if burglary happens, alarm will come. If earthquake happens, alarm will come. Something like that. So what's the probability that burglary didn't happen but earthquake happened? So what's the probability that the alarm will ring? So that is this one. If you look at false. Burglary didn't happen, earthquake did not happen. What is the probability that the alarm will ring? That is this case. And so on and so forth. So this is a Bayesian network. Now that you have a Bayesian network, you're supposed to write something like this, the simplified form. So here what are the random variables? You have J, M, A, B and E. So probability of J, M, A, B and E. So how do you write probability of J, M, A, B and E? So you start from the bottom, no? So you start from J. So you write probability of J, but J is dependent on A, so you write J given A. Then J is done. Probability of M is dependent on A, so you write probability of M given A. Now after M is done, go to A. So probability of A, but A is dependent on B and E. So probability of A given B and E. J is done, M is done, A is done. Write B, probability of B. There is no dependency, so directly probability of B, and then directly probability of E. So now in this example, we will see how this will be used using this Bayesian network. So there's a question. The question says find the it's asking us to find the probability of alarm sounding, but then neither burglary nor an earthquake occurred, but both John and Mary called. So you have alarm, you have burglary, you have earthquake, you have John, you have Mary. All the necessary information is given, so you just have to fill it in these. So alarm sounded means alarm is true. Neither burglary nor earthquake occurred means burglary is false, earthquake is false. Both John and Mary call is, so John calls is true, Mary calls is also true. So to those random variables you will assign true or false values, right? So if you write it in symbols, it becomes this. So small letters you do realize, right? So small letters represent nothing but this one. The capital letter is assigned true. The short form of writing this is small letter. We've seen it in the very beginning about the cavity. We've seen it in the very beginning. So in place of J, you will put the information. What is the information here? John. J is John calls, right? Is it true or false? So you will write J is equal to true. But instead of writing capital J equal to true, I can simply write small j. Small j means capital J is equal to true. And did Mary call? Yes, Mary called, so small m. Did alarm sound? Yes, alarm sounded, so small a. Did burglary happen? No, burglary did not happen. So I will put not small b. Or else I could write capital B is false. Or I could simply write not small b. That's why not small b. Earthquake also didn't happen, so not small e. Now that we have this, substitute in the expression that we derived. So it becomes like this. Just substitute all the values. Now that we have this, just look at the probability distributions and substitute the values. So for example, probability of John calling and alarm sounding, alarm ringing. So this is J given A, right? You will find it in this probability distribution. J given A. Given alarm sounded, what is the probability that John calls? So alarm sounded is A is true. So probability that John calls is 0.90. So you have 0.90 here. Then next, probability of given alarm sounded, what is the probability that Mary calls? So Mary, you'll have to look at this probability distribution. It is saying given small a. Given small a means alarm sounded is true. So A is true. So what is the probability that Mary calls? 0.70. So 0.7. So similarly, you just keep looking at the Bayesian network and substitute the values and finally calculate the probability. This is like a direct question. Every single piece of information is given. Now look at the next question. Not every piece of information is given. You just have probability. Find the probability of John calls. So it is just probability of small j. Probability that John calls. But we need more information, right? So when can John call? John can call anytime. Anytime in the sense it need not be that only when alarm rings John will call, right? So John can call. John could have called if there's an alarm, or John could have called if there was no alarm. So there are two cases. John calls if there was an alarm, or John calls if there was no alarm, right? So it's like alarm happened. So given alarm happened, what is the probability that John called? The other case is given no alarm happened. Given no alarm happened, what is the probability that John calls. So this is like an exhaustive list of John calling. But still, we need more information. We need to talk about burglary and earthquake as well. Here, alarm, small a means alarm is true. So alarm sounded. But alarm could have sounded in many possible ways. So burglary happened, earthquake happened. Burglary happened, earthquake didn't happen. Burglary didn't happen, earthquake happened. Burglary didn't happen, earthquake. So there are four possible combinations. Because burglary could be true false, earthquake could be true false. So there are four possible combinations. So probability of alarm sounding can be split into four parts. So those four parts are given burglary and earthquake happened, what is the probability that alarm sounded? The other case is burglary happened, earthquake didn't happen, what is the probability alarm sounded? Burglary didn't happen, earthquake happened, what is the probability that alarm sounded? Burglary didn't happen, earthquake didn't happen, what is the probability that alarm sounded? So this probability of alarm got split into four parts because there are four combinations. Alarm is dependent on B and E, and you have four combinations because burglary can take two values, earthquake can take two values. Now this is just the first part. The same story applies to the other part as well. So you have to expand the probability of no alarm. Alarm did not sound. So there are four possible combinations. Burglary, earthquake, burglary, no earthquake, no burglary, earthquake, no burglary, no earthquake. Now, having expanded all of this, you can finally see that you have all the necessary information. Now it is just a matter of looking at this Bayesian, looking at the probability distributions and substituting the values. So after substituting, after multiplying, after doing all of that, you'll get a number. There's one more question. Find the probability that there is a burglary given John and Mary call. So this is like reverse. We know that John and Mary called, but now you want to know whether burglary happened or not. So you're going from the bottom to the top. It's like you're going in the reverse direction. Because now you're inquiring about burglary, and what we know for sure is John and Mary, both of them called. So you can write it this way. Given that John and Mary called, find the probability of burglary happening. So there is a certain formula for this. So here the terminology is, this is evidence because we know John and Mary called. This is query because you're inquiring whether burglary happened or not. So we are inquiring if burglary happened or not, right? So let us multiply it with probability of burglary happening. We want to find out the probability of burglary happening, right? This part is fine. So probability of burglary happening and probability that both John and Mary call. This alpha came into the picture because probability of B given JM is nothing. Probability of burglary happening given John and Mary call is nothing but probability of burglary happening, John calling, Mary calling, divided by probability of John calling and Mary calling. So this is written as alpha, so you don't have to bother about the alpha. Or you could think of this like a formula, anything works. So you take the query outside and then it's like probability of query into probability of all the evidence. You can think of it this way as well. Or if you want to think about it logically, you can think about it that way as well. Alpha is just there to normalize the probabilities. So we want to find out if burglary happened or not. But this is fine. We have this number. We have probability of burglary. But we do not have probability of John calls and Mary calls. Both of them are calling. But we don't know if alarm sounded or not. So there are two possibilities. Alarm either sounded or didn't sound. And John calling and Mary calling, they are conditionally dependent or whatever. So John is calling, Mary is calling, right? It's not like they are dependent on each other. John can call whenever he wants, Mary can call whenever she wants, but both of them are calling here. So probability of John calling multiplied by probability of Mary calling, given that A happened. So here I wrote summation of A because there is a possibility that alarm might have rung or might have not rung. So I'll have to go through all possible cases. So I will go through A here. I will also go to not A. So summation of, so now I'll write A. When I open the summation, I will also write not A. So it will look lengthy. So I just wrote it in a short form notation. This is the same notation used in the slides as well. So essentially this became this. How did it become this? Because if both John and Mary call at the same time, you'll multiply those two probabilities because both of them are happening at the same time. But they're dependent on the alarm, right? So given alarm happened or given alarm didn't happen, so you have to find the summation. Both could have happened, so you have to add both the probabilities. But now the new thing here is probability of alarm. Alarm has again, but we know we are thinking that burglary happened. What is the probability that burglary happened, right? We're thinking that burglary did happen. So if you look at the Bayesian network, A is dependent on burglary and earthquake. Now you won't get 4 possible combinations, you'll only get 2 possible combinations because it is fixed. We are assuming that burglary did happen. So probability of alarm could have rung if there was an earthquake or if there was no earthquake. Burglary for sure we are assuming it happened, so we will not talk about the combinations of burglary. Earthquake could have happened, could have not happened. But alarm in one case must have rung or must have not rung. It depends on the summation. So finally the thing is you're going to expand the probability of alarm as well. So probability of alarm is dependent on burglary and earthquake. So you'll get probability of alarm given B and E multiplied with probability of E. Here you're not multiplying with probability of B because B is not changing, only E is changing. So earthquake may have occurred or may have not occurred. So you will be doing summation within this. So in one case you'll get E, in the other case you'll get not E, but B will remain small b because that is the entire question. The question is there is burglary. So you'll assume, okay, burglary happened, what is the probability? What is the probability that it happened? Now about this alpha, there's a formula for alpha. This question format is like you have some evidence and there is some query, right? Evidence is John and Mary called. Query is there is a burglary. So let's say you have M evidences and you have one query. So alpha is given by this formula. So let's say P1 is nothing but the probability of the query and all the evidences. P2 is nothing but not of the query and all the evidences. So alpha is nothing but 1 by the summation of P1 and P2. So alpha will nothing. So here the query is B and evidence is J and M. So alpha is going to be nothing but 1 by probability of the query and all the evidences, not of query and all the evidences. That is going to be my alpha. If you open the summation, you will be able to substitute all the values from the Bayesian network and you'll be able to find the probability of this question. The probability that there's a burglary given John and Mary call. This might just go around your head, but just stick with it. It should be doable. Next is Markov processes. So previously we've seen Bayesian networks, or in short Bayes nets or whatever. When they say it is static, it means it does not change with respect to time. But in Markov processes we have time. We are introducing time here. So time 0, 1, 2, 3, 4 and so on. And as time progresses, the state of the world also changes, and it is represented by st. So at time 0 it is state 0, s0. At time 1 it is state 1, so on and so forth. As time progresses, there will be a sequence of states that the world is passing through. And if you remember this structure I told you, right, Markov dependence or whatever. So because this thing looks like this, it's called Markov processes, Markov chain. So introduction of time is a new thing. The other thing is we have something called the Markov assumption. Markov assumption is this one. The next state is only dependent on the previous state. So given S1, S2, S3, S4 until ST, you give it the entire history of you give it the entire history of the states that happened before it. The next state will only depend on the previous state. So this is called the Markov assumption. So S3 will only depend on S2. It doesn't matter what S0 and S1 was. The other assumption is stationarity assumption. It just states that the transition probabilities remain constant. It's like if you're moving from one kind of a state to another kind of a state, that probability is going to be constant. It's not like as time passes that probability also changes. I'll show you an example, then you'll understand. So this is an example of Markov process. You have states, let's say sunny, cloudy and rain. There are three different states. So the weather here, the world is nothing but the weather. So the weather could be sunny, cloudy or rainy. So as time passes, the weather keeps changing, right? So the weather keeps transitioning from one state to the other. So these arrows that you see, right, they have probabilities. They are called transition probabilities. These probabilities are said to be constant. So that is the assumption. They don't change. That is the assumption here. The transition probabilities remain constant. So given at time t, the state is I, what is the probability that at time t plus 1, the state becomes j? The probability is a constant aij. So there will be a matrix where all the transition probabilities can be mentioned, or you can display it this way as well. So aij means transitioning from state I to state j. What is the probability? So sunny to sunny, if you go, then the probability is 0.6. We'll look at some examples. So there's a question. Find the probability that it will rain 2 days from now. Symbolically, you can just write find the probability of S2 equal to R. So we begin our day with S0. So 2 days from now means S1 and then S2. So S2 has to be raining. So the weather in this case, the weather in day 2 should be rainy. So S2 equal to R. Find the probability of that. But if S2 is R, then what about S1? If S2 is R, what about S1? So S1 means what was the weather on day 1? It could have been rainy, it could have been cloudy, it could have been sunny as well. So there are all possible combinations here. So if S2 is rainy, S1 could have been anything. So I'm taking a summation. It could have been sunny, it could have been cloudy, it could have been rainy. What about day 0? What about now? In the question itself, they've given an assumption. They've asked us to assume that the weather at day 0 is sunny. If you say probability is 1, it means it is certain. So day 0 is sunny. So you can't look at multiple options. It is given that day 0 is sunny, so it is pointless to look for combinations here. So the only thing that is changing here is day 1's weather. Is it sunny, cloudy, rainy? We look at all possible combinations. And then if you add all of this, you will get your probabilities. So what is happening? S0 is S, S1 is sunny, S2 is rainy. So S is nothing but state. So state of the weather. So day 0, day 1, day 2. Now how do you write the probabilities? If you look at this sequence, we are going from sunny to sunny and then sunny to rainy. So sunny to sunny, if you look at this, it is 0.6. So sunny to sunny is 0.6. And sunny to rainy is 0.1. Sunny to rainy is it 0.1? Oh, wait, I think I'll have to change the arrows. Just a minute. So sunny to rainy is 0.1. Sunny to cloudy is 0.3. So you keep looking at the transition, right? So you're transitioning. That's why they're called transition probabilities. So you keep doing that. So you get 0.1 into 0.6, 0.3 into 0.3, 0.3 into 0.1. So finally you get the probability. The probability that it will rain in 2 days from now is 0.18. There's another question. In the slide it was not completely solved, but they've given an idea. A probability that it will rain 3 days from now. If you follow the old approach, it will become longer and longer. You'll have to find many combinations. So the slides mentioned something called an efficient approach. Apparently there's an efficient approach in solving this. So representing this is simple. You just represent it. Probability of S3, probability that S3 is equal to R. So on day 3 you have rain. What about day 2? Day 2 could have been sunny, cloudy, or rainy again. So I can simply write it this way. And if you follow the previous approach, it will get longer and longer, because S1 also could have been anything. S0 is fine. We have S0 as sunny. So the efficient approach here is what they did. They've broken this down into 2 parts using rules of probability. So probability of A and B can be written as probability of A given B into probability of B. That's what they did. They used the rules of probability. So probability of A and B is nothing but probability of A given B into probability of B. But now the thing is, we have this one, we have this piece of information. It is nothing but the transition probability, no? Transitioning from X to R, that is there. But we do not have information as to what is the probability of S2 being equal to X, where X could be S, C or R, sunny, cloudy, rainy. So the idea that they gave is, apparently you can find the probability distribution of S2 using PS1, and that's it. They did not mention anything more. Interesting thought. I thought they would talk about this later, but I don't think they did. So I will leave it here as it is, and I'll move on. there's some theory about inference tasks. You could go through them once. Some theories there. Just 4 lines. And now they introduce something called the stationary distribution in a Markov process. They state that as time goes to infinity, probability of st equal to I means the state of the world at time t is I. So the probability of that is going to be a constant. So it means it's no longer dependent on the time. You can simply say that you can simply predict the probability of the world being in a certain state, irrespective of the time. And this is only valid when t goes to infinity. Like everything becomes stationary, nothing changes. If that is the case, if probability of the state of the world is not dependent on time, that would mean probability of st plus 1 equal to I is also the same, because as I said, as time changes, it doesn't matter, because as long as it's the same state I, the probability should be same. Again, this is only valid if t is tending to infinity. So this is like the stationary probability, the final probability, or whatever it is you think of it. So these are stationary probability distributions. So if you do some derivations, you'll finally get this equation. So this is the stationary probability, the probability of the world being in state I, and these are the transition probabilities, the transition probability of moving from state I to state j. So in order to find your stationary probability distribution, you just use this equation. So states in this example are sunny, cloudy and rainy, S, C and R. And AJI. So for example, ASS would mean what is the transition probability from sunny to sunny. So you just look at the Markov process thing and then write down the transition probability. So finally you'll get a set of equations. I tried solving it. My calculator says there are infinitely many solutions. So I do not know where to proceed from here. I thought of, since their probabilities, they should lie between 0 and 1, right? So I thought of doing something like that, but I didn't have the time. Even the slides don't proceed with this any further, so I left it there as it is. And there's some theory about how Markov models are this and that. Something about its restrictiveness. Go through the slides for that. HMM, okay. I did not solve any problem for HMM, so I think the meeting will be ending soon, in like 5 minutes. So this is like the shortest class probably. Yesterday I took 2-hour class. Anyways, HMM, hidden Markov model. It is very similar to Markov model, but there's some theory. Go through that. There were like 5-6 slides. Like there were 5-6 slides in the PPT talking about HMM, describing HMM and all those things. So you can go through the theory, but I'll talk about HMM itself. What does HMM have? It has some initial probability distribution. It has some set of hidden states. We'll come to what hidden is. And then as usual, you have transition probabilities, just like in Markov model. And then you have set of observables. Now these two things are new. You have hidden states, you have observables. And then you have emission probabilities. So it's not just transition probabilities, you have something called the emission probabilities. Now if you remember in Markov processes, what was there is, you only had the top portion. It was just the world moving from one state to the other. But in hidden Markov, what is happening is, you still have the same thing. You have the world that moves from one state to the other, But the thing is, you cannot observe that state. Those states are hidden. The only thing you can observe are observables. What are observables? Uh, Observables are nothing but the things that you can observe. There's nothing much in this. So it's like if the world is in state 0, you don't know if the world is in state 0 or not because it is hidden. But what you can see is something happened in the world that day or that at that instant. So let's say, I'll give you a small example. Let's say it is raining outside, but you were locked inside your room, so you don't know what's happening outside. And then suddenly someone comes into your room. Uh, their clothes were wet. They were so it means you can suspect that it rained outside, but you do not know. You were locked up inside your room. Your room has no window, so you have no way of certainly saying that it was raining outside. But all that you could see was you could see your friend coming inside dripping. His clothes were wet. So this is a simple example. So there's something called observations. There's something called hidden states. You do not know what exactly is happening, but you can infer from the observations. Oh, this is possibly uh, uh, this is something that's happening outside. This is possibly what's happening outside. This is the basic idea behind HMM. So hidden states. Again, hidden states are with respect to the world. World is moving from one state to the other, but you don't know what they are. Observables are something that you can see. For every given state that the world goes through, some observation occurs. You make some observation. So transition probabilities are the probability of transitioning from one hidden state to the other hidden state. And emission probability is the probability that you observe a certain observable given a certain hidden state. So if you look at the notations here, transition probability is at time t you are at state I, and the next time interval you are at state j. So you're transitioning from state I to state j. So AIJ, the transition probability. If you look at emission probability, given that at time t you're in state I, what is the observation made? At time t the observation made is k. K is an observable, and this is the observation that was made. So you have BIK. So at state I, you made an observation K. All these probabilities are bundled up and kept in emission probabilities. So you have an emission probability matrix, you have a transition probability matrix. Now you have some assumptions here as well for HMM. There's one assumption. There's something called the output independence condition or assumption or whatever. What it states is if you have any observation, that observation is conditionally independent of all other hidden states and observations given the current hidden state. So conditionally independent means something needs to be given, and that is the current hidden state. So if you look at the notation here, so these are all the states from all possible hidden states, S1, S2, S3 till ST. Capital T, different from small t. The small t is like current time. This is like all times. You collect all possible, you collect all the states and put them here. You collect all the observations and put them here. What were the observations made at time 1, time 2, time 3 and time capital T. This is equal to just this one. That is, this is happening because we made this assumption, the output independence assumption, which is nothing but this mouthful of thing. What is happening here is, at time t, if you make an observation that I happened, so here I is the observable. At time t, you observed I happening. I is the observable. Given that the hidden state was j, right? Given that hidden state was j, what is the probability that observable I was observed at the same time t? So these two things are equal. That is the assumption here. I think this is very much understandable. We also know why it is Bij. So in this case, state is so at state J, what is the observation made? So observable here is I. At state J, you made observation I. This part is fine. So this part is like it's like it doesn't matter. You can simply simplify this to this. So if you know you're at if you know that the hidden state is J, it doesn't matter what were the previous hidden states, and it doesn't matter what were the previous observations. So given that you're in a certain state, and given that you've made an observation, it doesn't matter what were the previous observations and what were the previous hidden states that the world has been through, because it is constant. From emission probability matrix, you will get this value. So this is the assumption, output independence assumption. I think when we solve problems, this might be useful. I do not have any problems here with me right now. So I just have an example. How does HMM look like? So I just extended the previous example. The previous example was Markov model, right? In hidden Markov model, you have instead of states, you have hidden states and you have observables. And transition probability, it's already here. There's nothing new for that. But you have something new here. So emission probabilities. So in pink, I've mentioned the new aspects. So these things different. These things make HMM different from Markov models. So transition probabilities are with respect to the transitions from one hidden state to the other hidden state. So I was telling you, you could be locked up in a room, and then you have a friend who comes from the outside. So he could either be wet or he could be dry. So that's the only thing you could observe, but you don't know if it's sunny outside, if it's cloudy outside, or if it's rainy outside. These things are hidden. The only thing that you can see is the state in which your friend is. Your friend comes from the outside. You can observe if his clothes are wet or if his clothes are dry. So emission probabilities. So its size will be number of hidden states cross number of observables. So you have 3 hidden states and then you have 2 observables. So it's a 3/2 matrix. So what do these probabilities mean? It's like given that the hidden state is sunny, what is the probability that my friend is going to my friend's clothes are wet? Like if you look at this notation, right? Given a certain state, what is the probability that the observation K was made at the same time? And if you look at, for example, this one, given that my friend was no, given that the hidden state is oh wait, this is not dry, no? Sunny, cloudy, and rainy. Yes, it's a mistake. It's supposed to be rain. So 0.2 is nothing but probability. Given that the hidden state is rainy, what is the probability that my friend emerges dry? So this is an introduction to HMM. We'll solve problems tomorrow on HMM. Fine. So I shall end the meeting now. I shared this. I will reshare the document because there are some small minor changes. No? So I'll reshare it again. So there goes the meeting. I'll cover the rest of the topics tomorrow, hopefully, and then I'll start French also tomorrow. Okay, goodbye, good night.